Welcome to topic 11.8. This is resistor capacitor RC circuits daily video 3, where we're going to analyze our steady state conditions for various open and closed switch scenarios. My name is Dr. Kelly Miza. I'm from Delaware Valley Regional High School in Frenchtown, New Jersey. So first, let's do a little bit of review. If you were here for last video, we went through our nice little RC circuit and we derived our lovely equations for charging our capacitor. And they looked a little something like this. Now, if you actually did that exercise I told you to do of doing that integral with this different bottom limit to go for a discharging capacitor, you should have gotten these equations. Woo! So in general, if we're charging our capacitor, whenever you have this 1 minus e to the negative t over RC behavior, that means it's growing and then it has that asymptotic behavior up until our maximum voltage or our maximum charge. And if we have that e to the negative t over RC behavior, that means we're rapidly decaying to 0. So when we're charging our capacitor, the voltage and the charge across our capacitor are increasing, and the voltage and the current through our resistor are decreasing because the capacitor is stealing it all. Whereas when we're discharging our capacitor, the voltage and the charge in our capacitor are rapidly decreasing because all of the charge is leaving, whereas the voltage and the current through our resistor are also decreasing because it's the capacitor that's making that happen. So today we're going to look at what happens to these equations as time goes to infinity. So after a really long time, this is what we call the steady state. We're actually also going to look at a couple situations where, like, once you flip the switch, like right when it closes, what does the circuit do as well? Alrighty, so here's those equations again. And so right now I want you to think about if I make t really, really big, like infinity, for example, what happens to these equations? So when I have e to the negative t over RC, this is eventually going to decay down to 0. E to the negative large number, remember that's like 1 over e to the huge number, so that's going to go to 0. So this voltage across a charging capacitor, it's going to be the voltage of the battery once it's fully charged. Same deal with this guy. This term is going to go to 0, which is going to leave us with Q equals CV, as if it was just there by itself. For our resistor, when we're charging our capacitor, this term is going to go to 0. And the current is also going to go to 0 because the capacitor is like, nope, I'm full, no more, thank you. When we're discharging our capacitor, our voltage after a really long time, our capacitor is empty. There's nothing there. So the voltage is 0, the charge is 0. And because there's no charges moving, that means the voltage and the current through the resistor are also 0. All right, neat. So let's look at an actual example to see, like, okay, what do we do with that? This is my favorite analogy. You love chicken nuggets, right? You have a big old box of chicken nuggets and you open your box of chicken nuggets and you're like, nom, 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 nom. And you eat all your chicken nuggets. And at first you're like, yes, I love chicken nuggets. I'm going to eat them really fast. Nom, 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 nom. But then as you start eating more chicken nuggets, you're like, oh man, I'm losing steam. I'm losing steam with my chicken nuggets. Until eventually you're like, I cannot physically consume any more chicken nuggets. That's how I think of capacitors. So your capacitor is like, charge, yes, give me all that charge. Yum, 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 yum. Until eventually it's like, please, no more charge. I can't take it. And at that point, charge in your circuit stops flowing because there's nowhere for the charge to go. The capacitor is closed for business. So all of these little charges up here are no longer moving, which means there's no current through that resistor. That current through the resistor is 0. Your resistor might as well not even be there for all it's behaving in the circuit. So because there's no current flowing through this resistor, that means there's no voltage drop across this resistor. So your nice full tummy of chicken nuggets and charges has the same potential as the battery. So let's look at an example with actual numbers. So we have this lovely RC circuit over here. Let's move our switch to position number 1. And when we do that, now we are starting at an uncharged situation. And now we want to make our capacitor charge. So as soon as you close the switch, charge is like, yes, let's go. So as soon as you close that switch, the capacitor is completely empty. So immediately when you close that switch, it's almost as if that capacitor is not there. It's not acting as a roadblock anymore. It is like, yes, give me your charges. I will take all of them. So when a capacitor is totally empty, it behaves the same way as a wire, which means when I'm asking questions about a resistor, as soon as I close that switch, it's as if it's not even there. It's as if this is just a wire. So it's just a resistor with the battery. Well, that means that the voltage across the resistor is the voltage of the battery, which is 10, which means I can find the current from Ohm's law. From Ohm's law, it's V over R. So my current is going to be 10 over 100 ohms, which is 0.1 amps. So now let's wait a long time. Our capacitor is like, all right, I'm full, I'm done, no more, please stop. When your capacitor is full, no more charge can pass through this point. So when a capacitor is full, it acts as a roadblock, which means there's no current going through the resistor, which means there's no voltage across the resistor, which means the voltage is 100% going across that capacitor, like we just said on our chicken nugget adventure. And if I know the voltage across my capacitor and its capacitance, I can figure out the charge that got stored on that capacitor using our Q equals CV. So if my capacitance is 100 microfarads and my voltage is 10 volts, I end up getting 1 millicoulomb of charge stored across that. Okay, so we ate all of our chicken nuggets. We have a full belly of charges. Our capacitor is like, yes, I love charge. This is so good. I'm so full. Okay, woo. And then you're like, maybe I made a mistake. Blah, 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 blah. There goes all of your charges. Now they can go redistribute themselves, neutralize your circuit. So all of your charges at first are like, yes, I want to go back to the other side. And eventually they start losing steam. And then once all of the circuit situation is nice and neutral, nothing's flowing. There's no charges. Charges aren't moving. There's nowhere for them to go. So that means what initially started as a current out of your capacitor through your resistor, it decays to 0 as you run out of charges to push back the other way. So now we have a fully charged capacitor. That's where we're starting in this example. Let's move that switch to position number 2. So we're going to discharge our capacitor now. So as soon as we close that switch, remember, this capacitor had a charge of 1 millicoulomb. It had a voltage of 10 volts. So as soon as we close that switch, our resistor thinks that this is a battery. Like our resistor doesn't know any better. It's like, oh, sweet, I have 10 volts. Yay. Which means there's 10 volts across my resistor because these are in parallel right now. And also technically series, but parallel right now. So that means I, V over R, is also 0.1 amps. But now it's going the other way. Now it's coming from the positive terminal of my capacitor. So now it's going this way instead. After a really long time, our capacitor is empty, which means there's no more charge to move, which means there's no current. So there's no voltage across the resistor, and there's no voltage across the capacitor because everybody's empty. We're just hanging out, we're just neutral, nothing. Let's practice. Okay, so let's throw in an extra resistor to this example. So we're going to add an extra little resistor right here and see how that changes. So right now we're initially uncharged. So I'm going to close my switch. So the second I close that switch, my capacitor is empty. My capacitor is empty. It's like, give me your charges. Let's go. I'm hungry. So our capacitor acts like a wire. So as far as you're concerned, immediately after you close that switch, this capacitor is just a wire. You have 2 resistors in parallel. Cool. Your capacitor is totally empty. It acts like a wire. Voltage is 10 across each resistor, which means the current through R1, V over R, is 10 volts over 100 ohms. That's 0.1 amps. Current through R2, which is 10 volts over 200 ohms, is 0.05 amps. Then, after a really long time, your capacitor is full. It's closed for business. Your capacitor is like, no charges are allowed to come this way. No, thank you. So that completely cuts off this branch from our circuit. So R2 is also out of business. R1, on the other hand, still has a direct line to the battery. So R2 completely cut off. no current going through there because the capacitor is closed. V equals 0 across R2 as a result. But R1 is still in business, still connected to the battery. And the capacitor, because it's full, is also 10 volts connected to the battery. Because remember, when there's no current, it's as if this resistor might as well not even be here. It's just a wire at this point, just taking up space. So that means there is still current through R1. It's 10 volts over 100 ohms. It's still 0.1 amps. So R1, its current actually doesn't change. It's only R2 because R2 is the one that's connected to the capacitor, which means once we're fully charged up, I can figure out the charge on my capacitor as well. So we have our 100 microfarads. It has a voltage of 10 volts, so it gets 1 millicoulomb of charge as well. All right, now let's look at the situation where we're fully charged up, we're ready to go, and I'm going to open that switch. So now that I've opened that switch, my capacitor is behaving like the battery. My capacitor has that 10 volts and it's ready to pump that out through this little circuit. So as soon as I open the switch, my capacitor behaves as if there was a 10 volt potential difference across R1 and R2. But in this situation, once I open that switch, looking at how my charges are going to redistribute themselves, R1 and R2 are in series now when we open that switch. So that means they have an equivalent resistance of 300. And their current, because they're in series, is going to be the same. So they have 10 volts together with a resistance of 300 together. So they all get 0.033 amps immediately after you open that switch and it starts discharging. But then after a long time, your capacitor runs out of charge. It's like, all right, I'm out, which means there's no more current, which means there's no more potential difference across your resistors or across your capacitor because it's empty. So what should we take away from this? When we are looking at super long time in the future, like time goes to infinity, what we call a steady state after a long time, as you'll see it in questions, uncharged capacitors, they act as wires initially, as soon as you close that switch when they're empty. And then as your charge builds up, once they're full, they're like, no more. They act as roadblocks. Your resistors act like wires when your capacitor is full, and they act as roadblocks the rest of the time. And with that, thanks. Sorry if you're now craving chicken nuggets.